All right, let's try that again. So we got a system with two masses, mass 1 and mass 2. Mass 2 is hanging. Mass 1 is free to slide on a tabletop. We're going to say that the system is a rigid system, which means that the rope is unstretchable. We're going to say that it's a frictionless tabletop. Otherwise, the friction acting back on that mass 1 would be causing negative energy to be delivered to the system, or we'd be getting robbed of energy from the system. And we're going to say that the pulley is massless, which of course makes sense, because if we don't make it massless, then rotational inertia would be a part of the pulley, and it would mess up the way things are going to move. So we're going to make all these kinds of assumptions. We're also going to say that since this is a massless system, these two objects, not a massless system, it's a massless pulley, and it's a massless rope. I didn't say that. Two objects are connected by a massless rope. Okay, and these are, it's a lot of assumptions that are obviously going to make this less realistic, but they're assumptions that we're going to make at this grade level because it simplifies things. Making the rope non-massless requires calculus. Making the pulley non-massless also requires calculus, but an understanding of moment of inertia. Making the system non-rigid, well, that's a whole other kettle of fish. Frictionless, we could probably deal with if it had friction. Now, if this rope is not stretchable, though, we could say that V final for object 1 is going to be equal to V final for object 2. And that would be equal to, you know what, since they're the same value, we could just say that V final for the system would be the same as the other two. That's going to help us later on with simplifying things. What I'd like to do is find that impact speed, that final velocity of mass 2 hitting the ground. So it says that up in the givens. So what we're really looking for is this VF. The way that I'd like to tackle it is by conservation of energy this time. I know that we could do it by a dynamics argument, but I want to set it up like this. I'm going to write E total initial equals E total final in the very first row. Notice that I'm not writing E total 1, E total 2, because I'm using the 1 and 2 indices to identify object 1 and object 2. I'm going to use I and F to identify before and after. And so we got to be careful about that, because we've got two objects both experiencing a before and after. But if I expand this thing out, and I'll keep my equal sign centered, at least for now, as long as I can say that I've got E total 1 initial plus E total 2 initial. I've got E total 1 final plus E total 2 final. If I expand that out further, and I'll give myself lots of breathing room on either side of this equal sign, that means that I would have an EG1 initial plus EK1 initial plus EG2 initial. I'll make sure that my eyes are nice and bold there. Plus EK2 initial. And then on the final side, the same pattern, EG1 final plus EK1 final plus EG2 final plus EK2 final. And actually, this is a good starting point for conservation of energy for both of these. Of course, we could keep on stringing these things out. If we had friction, I'd have to say, somehow I'd have to work in work done by friction into this, either as a negative value on the left-hand side, as a positive value on the left-hand side or negative value on the right-hand side. I'd have to work in, if I wanted to have rotational energy, rotational motion energy, I'd have to work in this idea of the non-massless pulley being rotational energy before and after for the pulley. But we're going to get to skip all of that. As I look at this, though, and I want to simplify it, I could take this through and make like a super generalized equation where I would be looking for EK final. You know what, maybe let's just expand it out so that we can see all the information under the hood here. But if I'm going to do that, I'm going to have to go all the way over to the left-hand side. So if I say EG1 initial is mass 1 AGH1 initial plus EK1 initial 1/2 M1 V1 initial squared plus mass 2 AGH2 initial plus 1/2 M2 V2 initial squared equals, and do the same pattern on the other side, only with H1 final. So get your 1s and your 2s and your I's and your F's all straight. And from here, I could recognize that really and truly, this V2, oh, sorry, over here, V1 final, remember, I said V1 final and V2 final are actually going to be the same value for a rigid system. I could recognize that this value here is going to be VF, and this value here would just be VF. I won't white it out, because I want to show what I've done. But then other things that I could do to simplify here, I could zero things out. Like maybe on the left-hand side, is there anything that should be zero here? If this thing starts from rest, so I could add that information in. I guess I never really said that, did I? I could say V1 initial is 0 meters per second, and V2 initial is 0 meters per second. I guess I never did explicitly, so I'll pull that up there. I never did explicitly say this. I kind of just thought it in my head. They don't have to be 0, we can see that, but in the case where they are 0, what can I get rid of? Yep. Yeah, those guys could disappear. I'm only just going to cross them out because this is a special case where it starts from rest. It could be that I don't get to cross those out in the non-special case, right? Is there anything else that should zero out? Maybe even on the right-hand side. Yep. Okay, so if this thing's going to hit the ground, H2 final is going to be 0. Is there anything else that's going to zero out? I don't actually see anything that truly goes to 0 other than these ones, but there is something else that I notice. The object on the table, if I'm thinking this out, does the object at the table stay the same height the whole time? Doesn't that mean that those two values are actually the same value? So they're not truly 0, but if I'm thinking about how to simplify this thing, I can get rid of them. I'm going to circle them just so that, and you can make a little note to yourself, that it's not truly zeroed. It's just the same as on the right-hand side. Maybe I'll make a little note to myself. Same as in the after scenario. Okay, so it's the same values in the after scenario. That's why we're getting rid of it, not because it's truly 0. So I haven't put 0 at the end of my stroke because I'm trying to make it so that I can understand what's going on here later. Anyway, mass 2 Ag, that got rid of a lot of information. And that's not actually a special case so long as we're talking about this specific situation, right? Well, I guess it's special in that way. We're all a little special. 1/2 m1 vf squared plus 1/2 m2 vf squared. And oh my gosh, that really dropped down to a lot less. What are we even looking for here? We're looking for vf. So I want to factor some things out. M2 AGH2 initial equals, looks like I can pull out 1/2. Oh, this is weird, because I'm trying to isolate for VF. Mass 1 plus mass 2. And then I think to myself, well, how am I going to get this VF all by itself? Well, it seems to me that it makes sense that I'll multiply both sides by 2. So I got 2 M2 AGH2 initial. And I also think I'm going to divide by M1 plus M2. Right? I'm talking about dealing with this and dealing with this. Sorry, I'm off screen. And that's going to be equal to VF squared. But then just because I'm kind of on a roll here, maybe I'll get that VF square rooted. Make that look all F-ish. And then we can plug in our values. We can say, okay, well that means that VF is equal to 2 times the mass of the system, oh not the mass of the system, mass 2, 10 kilograms, times 9.81 meters per second squared. Notice that it's just 9.81, it's not positive or negative or anything because we don't care about reference frames, we care about magnitude for energy. H2 initial. We never even talked about that. We're starting off at 2 meters for this mass. We're going to finish at 2 meters. That's why we can make that earlier claim. Start off at 0.5 meters. We finish at 0 meters. So we got this 0.5 meters going in here. 0.5 0.00 meters divided by mass 1 plus mass 2, which is the mass of the system. So 5.00 kilograms plus 10.00 kilograms, all rooted. And I get a number that starts with 2. What do you guys get? Audrey, what do you get? 55734. Nice. Meters per second. And we can round it off to, I think it was 3 sig figs way back in the beginning, 2.56 meters per second. And of course, we could write a nice little therefore statement. Therefore, the mass 2 impacts the ground at 2.56 meters per second.